Module 2, Lecture B, Loops and Iteration. By the end of this lecture, you will be able to use for loops to repeat calculations over sequences of engineering values. Use while loops for controlled trial calculations with clear stopping conditions. And accumulate totals, maximums, and counts from repeated civil engineering computations. For loops. Sequence iteration. A for loop processes a collection of values one at a time, applying the same operation to each value in sequence. This is useful in engineering because many calculations involve repeated work across measurements, design options, or locations. By automating the repetition, loops improve efficiency, consistency, and reduce errors, especially with large datasets. Sequence iteration means working directly through a set of meaningful values instead of manually counting steps. In a loop, each value becomes the input for one calculation, such as checking a limit or converting units. The loop handles the progression automatically, so engineers can focus on the calculation logic, especially when applying the same operation to large datasets. Sequence iteration helps engineers apply the same process consistently to every value in a dataset, supporting repeatable and defensible analysis. A for loop reduces manual errors, helps ensure no data points are missed, and keeps attention on which values to process, what operation to repeat, and what result is needed. This disciplined approach connects real-world data with the logical steps required for efficient computational problem solving. Python code sequence iteration. This example shows how to iterate through a sequence of engineering values, processing one rainfall intensity at each loop step. The results are kept brief, so beginners can focus on the basic pattern without extra complexity. A list is created to store rainfall intensities of 20, 35, 50, and 65 millimeters per hour. These values represent different rainfall scenarios and make it easy to process each one when calculating runoff. The code defines the watershed area as 1.2 square kilometers. This represents the land area that collects rainfall and is needed to calculate runoff during rain events. The runoff coefficient is set to 0.75, meaning about 3/4 of rainfall on paved urban surfaces becomes surface runoff. This helps estimate water flow by accounting for rainwater that does not soak into the ground. The code first prints a brief message to explain what the program is about to do. It tells the user that the following calculations will estimate runoff values from a series of rainfall intensities, making the purpose of the loop clear. The process loops through each rainfall intensity and uses the rational method to estimate flow. For each case, it multiplies 0.278 by the runoff coefficient, the rainfall intensity, and the watershed area to get flow in cubic meters per second. This makes it efficient to calculate flows for multiple rainfall scenarios. This line displays a formatted console message for each iteration. It reports the rainfall intensity in millimeters per hour and the resulting flow in cubic meters per second, with the intensity aligned neatly and the flow rounded to 2 decimal places. The code counts how many rainfall intensity values were processed by finding the length of the intensity list. That total shows how many values the loop went through and confirms that each one was handled. The code prints a brief summary showing how many rainfall intensity values the loop processed. It uses the size of the rainfall list to insert the count into the message, confirming that all expected values were included. This script uses the rational method to estimate runoff flow rates for several rainfall intensities. For each rainfall value, it applies a fixed watershed area and an urban paved runoff coefficient, then prints the resulting flow in cubic meters per second. After processing all values, it reports how many rainfall intensities were calculated. Iterating engineering values. A for loop is useful in engineering when the same calculation must be repeated across related values. It processes each value in sequence, such as beam spans or soil depths, using the same logic every time. This reduces repetitive instructions, improves clarity, and helps prevent errors. In engineering, datasets often contain repeated values, such as locations or time steps that need the same kind of analysis. A for loop processes each value in order, applying a consistent calculation to every item. This helps engineers perform complete, uniform checks and support reliable professional results. A for loop repeats the same analysis across many design cases, such as different pipe sizes or pavement thicknesses. As the dataset grows, the loop keeps the calculation process consistent and accurate. This lets engineers focus on interpreting important results while the computer handles repetitive work. Python code, iterating engineering values. For loops repeat the same engineering calculation for each value, keeping the process consistent and the results organized for easy comparison. The code defines several beam span lengths in meters for analysis: 4, 5.5, 7, and 8.5 meters. These values can then be used one by one to perform calculations for each beam length. Begin by creating an empty list to store the deflection estimates for each beam span. As the loop runs, each calculated value is added to this list, keeping the results organized for later review or analysis. For each beam span, the deflection is estimated from its length. The calculation uses a simple rule. The deflection in millimeters is 0.08 times the span squared, giving a quick measure of how much the beam may bend under load. The code saves each calculated deflection by adding it to a list of estimates. This keeps the results organized and available for later analysis or summary. The code prints a short result for each span, showing the span in meters and the calculated deflection in millimeters. This makes the span and deflection relationship easy to read and compare across different cases. The code counts the number of design cases by finding how many deflection estimates were stored. This total matches the number of spans processed, so it shows how many scenarios were checked in the loop. To find the largest estimated deflection, use the maximum function on the list of deflection values. It identifies the highest value, showing the most extreme deflection case in the engineering analysis. The code prints a brief engineering summary of the deflection results. It reports how many span cases were checked, then shows the maximum deflection found. This gives engineers a quick view of the calculation count and the worst-case result. This script estimates beam deflection for several span lengths using a simple calculation, 0.08 times the span squared. It processes each span, records the deflection, and prints both values in millimeters. Afterward, it reports how many spans were checked and the largest deflection found, making the results easy to compare. Looping engineering sequences. In engineering, a for loop is useful when the same calculation must be applied to a known sequence of values, such as station points or pipe diameters. It automates repeated work, improves consistency, reduces errors, and makes the workflow easier to update when project data changes. A for loop lets you repeat the same engineering calculation across multiple site areas without rewriting the process each time. For example, it can calculate runoff for drainage areas with different sizes or slopes, and the same idea applies to stress checks, roadwork volumes, and foundation pressures. The loop handles repetition, but sound engineering judgment is still needed to verify the results. When using for loops with engineering sequences, think carefully about what each item represents and whether its order matters. Some data, such as elevations or hourly temperatures, must stay tied to the correct location or time, while other independent calculations may be less order sensitive. Clear sequencing helps make results traceable, accurate, and easier for teams to check and communicate. Python code looping engineering sequences. For loops help repeat engineering calculations efficiently. They work with sequences of related project values so each item can be processed in the same consistent way. A list is created to store the acreage of each subcatchment area. These area values are used later to calculate runoff, and keeping them together makes it easy to apply the same calculation to each subcatchment in a loop. A list of runoff coefficients is defined for the subcatchment areas. Each coefficient shows what fraction of rainfall becomes runoff, which is needed for the rational method. Keeping the coefficients in a list makes it easy to match each one with its corresponding area during processing. The design rainfall intensity is set to 2.1 inches per hour and used for all subcatchment runoff calculations. Defining this value once keeps the calculations consistent and makes it easy to update if needed. First, create an empty list to store the runoff values calculated for each subcatchment. This gives the loop a place to collect and organize each result as it is produced. The process pairs each subcatchment area with its runoff coefficient using the zip function, then calculates runoff for each pair. It multiplies the coefficient, rainfall intensity, and area to estimate flow in cubic feet per second using the rational method. The code saves each computed runoff value in cubic feet per second into a results list. This keeps the rational method outputs from the loop organized, so they can be reviewed and summarized for each subcatchment area. To find how many subcatchments were processed, we count the computed runoff values stored in the results list. This count shows how many subcatchments had runoff calculations completed. Total runoff is found by adding the runoff values from all subcatchment areas. The result is one combined water flow rate, measured in cubic feet per second. To identify the largest runoff result, use the maximum function on the runoff values. It finds the highest value, representing the peak runoff in cubic feet per second, across all subcatchments. This peak value is important for engineering assessment and design decisions. This line prints a console message to show that runoff has been calculated for each subcatchment. It labels the results that follow, so the reader understands the numbers are the computed runoff values for different areas. The code loops through the computed runoff values for each subcatchment, using enumeration to attach a subcatchment number to each value. It then prints each runoff in cubic feet per second, rounded to 2 decimal places. This creates a simple, readable output for checking the results. This line displays the total runoff by adding all individual subcatchment runoff values. The result is rounded to 2 decimal places and reported in cubic feet per second. The code reports 2 results from the runoff calculations: the highest runoff value found across all subcatchments and the total number of subcatchments processed. It finds the maximum from the computed runoff results, then counts how many results are in the list. This script uses the rational method to estimate runoff for multiple subcatchments. It combines each area's size, runoff coefficient, and a fixed rainfall intensity to calculate individual runoff values. It then reports each result along with the total runoff, the largest runoff value, and the number of subcatchments analyzed. Controlled while loops, trial calculations. Engineers often use controlled while loops to test and refine design assumptions until requirements are met. For example, a pipe diameter estimate can be adjusted through repeated trials until it satisfies design conditions. This matches real engineering practice, where guesses are checked against standards and revised only as long as needed. A controlled trial calculation needs a clear loop. Start with a reasonable trial value, check it against the required engineering criteria, then adjust if it does not meet the goal. The value should be practical enough to avoid wasted effort, but flexible enough to explore better solutions. For example, a drain that lacks capacity may need a larger size, while overly conservative excavation support may be tested with wider spacing while maintaining safety. Trial calculations in a while loop combine repeated testing with controlled decision-making. Each calculation can respond to earlier results, while keeping design changes clear, safe, and traceable. In engineering, this helps ensure choices such as adjusting sizes or volumes are based on both sound numbers and clear reasoning, guiding designs toward practical solutions. Python code. Trial calculations. Controlled loops help organize engineering trial calculations by testing one design assumption at a time. Clear stopping conditions ensure the process ends when the goal is met and prevent unnecessary repetition. Set the target flow rate to 180 liters per second, then begin with a trial pipe diameter of 300 millimeters. If that size is not sufficient, increase the diameter in steps of 25 millimeters until the required flow capacity is met. The setup begins by limiting the pipe diameter to 600 millimeters, so the loop cannot run endlessly. A trial counter is set to 0 to track the number of iterations, and the pipe capacity starts at 0 liters per second. The capacity will then be updated during each loop based on the current trial diameter. The loop keeps trying new diameters while the estimated capacity is still below the required flow, and the diameter remains within the allowed maximum. On each trial, it updates the count and estimates capacity from the square of the current diameter times a constant factor, giving an approximate flow in liters per second. The code reports each trial by showing the trial number, the pipe diameter, and the calculated flow capacity, rounded to 1 decimal place. If the capacity is still too low, it increases the diameter by the chosen step size and tries again. This lets the loop adjust the design only as needed until it finds a diameter that meets the required flow. The code compares the calculated capacity with the required flow to decide whether the design works. If the capacity is high enough, it reports the accepted diameter and how many trials were needed. If not, it reports that no suitable diameter was found within the search limit. The script tests pipe diameters to find the smallest one that can carry at least 180 liters per second. It begins at 300 millimeters, increases by 25 millimeters each trial, and stops if the required capacity is reached or the diameter reaches 600 millimeters. Capacity is estimated as increasing with the square of the diameter, and the script reports each trial before giving either the accepted diameter and trial count or noting that no acceptable solution was found. Stopping conditions. A stopping condition tells a while loop when to stop repeating calculations. This is important in engineering problems where the number of attempts is not known in advance, such as adjusting a design until it meets a required check. The loop begins with a guess, runs the calculation, tests the result, and either stops or tries again with an updated value. A clear stopping condition keeps the process focused on the engineering goal and prevents endless repetition. While loops need clear stopping conditions because they continue until their test becomes false. A condition that is too loose can stop too early, while one that is too strict can run too long or never finish. In engineering tasks, such as setting a drainage channel slope, the loop should stop only when the design requirement is met. Good stopping conditions combine sound numerical logic with practical judgment, making results safer and easier to review. A robust engineering while loop should include more than one stopping condition. One condition marks successful completion, such as reaching a target or safety requirement, while another prevents wasted or unreasonable calculations, such as too many trials or no further improvement. Together, these conditions make iterative calculations more reliable and consistent with engineering practice. Python code stopping conditions. Use a footing width trial calculation to demonstrate how a while loop repeats until a stopping condition is met. The loop should keep testing widths until it finds a successful design, while also including a safety stop to prevent endless repetition if no acceptable width is found. The allowable bearing pressure is set at 180 kilopascals. This is the maximum soil pressure permitted under the footing to keep the foundation design safe and stable. Start with an initial trial footing width of 0.8 meters. This small starting value allows the width to be increased iteratively until it satisfies the required design conditions. Set the column load to 900 kilonewtons and the footing length to 2.5 meters. These inputs are used to calculate the bearing pressure on the soil, helping verify that the footing design meets safety requirements. The footing width is increased in steps of 1/10 of a meter for each trial. A maximum width of 3 meters keeps the design within a practical size, while a limit of 30 trials prevents the loop from running indefinitely if the required conditions are not met. Begin by setting the trial count to 0 to track each attempt at sizing the footing width. Then, calculate the initial bearing pressure by dividing the column load by the footing width times the footing length. This pressure is compared with the allowable bearing pressure to judge whether the footing width is adequate. The loop keeps testing wider footing sizes while the bearing pressure is still too high and the trial limit has not been reached. With each attempt, it increases the trial count and adds a fixed amount to the footing width, which helps lower the pressure. The process stops once the pressure is acceptable, or the maximum number of trials is reached. After the footing width is adjusted, the code recalculates the bearing pressure by dividing the column load by the updated footing area. This checks whether the new width satisfies the required pressure limits. The code checks whether the footing width has become larger than a preset practical limit. If it has, the loop stops right away, so the design process does not continue using unrealistic footing sizes. After the loop ends, we check why it stopped. If the bearing pressure is at or below the required limit, the design is acceptable. We also confirm the footing width has not exceeded the maximum allowed value, showing whether the loop ended because the pressure became safe or because a size constraint was reached. The output summarizes a controlled while loop used to test different footing widths. It reports how many trials were completed, then gives the final footing width to 2 decimal places and the final bearing pressure to 1 decimal place. Together, These values show the result of the loop and whether the trial process reached an acceptable stopping point. After the loop ends, we check why it stopped. If the bearing pressure is acceptable and the footing width is still within its limit, the loop ended successfully. Otherwise, it stopped because a safety limit was reached. This makes the loop stopping reason clear. This script uses trial and error to find a suitable footing width for a column load. It starts with a small width, increases it step by step, and recalculates the bearing pressure until the pressure is within the allowed limit. The process stops either when a safe width is found or when a maximum number of trials or width limit is reached. The final output reports the trials, footing width, pressure, and reason the process stopped. Convergence checks. Convergence checks help controlled while loops decide when repeated trial calculations are accurate enough to stop. In problems without a direct solution, an initial estimate is refined until the latest result changes very little or meets the design requirement closely enough. These checks prevent loops from stopping too early with unreliable answers or running longer than necessary. A convergence check should match the scale and purpose of the engineering problem. In some cases, it is enough for repeated estimates to change very little. In others, the result must be within a practical tolerance of a design requirement. The tolerance should be acceptable, not infinitely precise, because limits that are too loose can hide errors, while limits that are too strict can waste computation. Good convergence criteria reflect measurement precision, design standards, and the consequences of being wrong. Convergence checks help ensure an iterative process is working and does not run forever. A good while loop should define both success and failure conditions, such as limiting attempts or stopping when results become unrealistic. In engineering calculations, reliable loops combine mathematical criteria with professional judgment so trial processes stay controlled and meaningful. Python code, convergence checks. Controlled while loops are used to repeat a process until it converges. An engineering tolerance defines how close is acceptable, while safety limits stop the loop from running forever. We set the basin's target storage volume at 500 cubic meters. This fixed goal guides the iterative adjustments, helping the calculations move toward the desired capacity. We begin the iterative process with an initial basin storage estimate of 120 cubic meters. This reasonable starting value helps the calculation move efficiently toward the target storage volume with fewer iterations. Begin by setting a tolerance that defines how close the estimated storage volume must be to the target. Then set a maximum number of trials to prevent the process from running indefinitely. A trial counter starts at 0, so progress can be tracked and the iteration can stop when needed. First, we measure the initial error by finding the absolute difference between the target storage volume and the current estimate. This shows how far the estimate is from the desired value and provides the starting point for the convergence process. The loop runs while the error remains above the tolerance and the trial count has not reached its limit. Each pass adds 1 to the count, then adjusts the storage estimate by 45% of the gap between the target and current storage, moving it gradually toward the target. The storage estimate is refined by adding a calculated correction to move it closer to the target. After each update, the error is recalculated as the absolute difference between the target and the new estimate. This error is saved for the next loop iteration, allowing the process to continue until the tolerance is met or the trial limit is reached. Convergence is determined by comparing the latest error with the chosen tolerance. If the error is less than or equal to that tolerance, the estimate is considered close enough to the target value, so the process has successfully converged. The output summarizes the basin storage convergence check by showing the final estimated storage, the target storage, and the final error. It also reports how many trials were used and whether the result met the required tolerance, indicating whether the iterative process successfully converged. This script checks whether an estimated basin storage volume converges to a target of 500 cubic meters. Starting from an initial guess, it repeatedly adjusts the estimate by using 45% of the remaining difference. The process stops when the error is within 2 cubic meters or after 20 trials. It then reports the final estimate, remaining error, number of trials, and whether the tolerance was reached. Accumulation. Running totals. Running totals start at 0 and grow as each new value is added. In engineering, they help combine sequential data into one useful result, such as total asphalt needed or rainfall accumulated during a storm. Because each update keeps all previous contributions, running totals make large or incoming datasets easier to manage and interpret. Running totals help engineers track data as it is collected, such as loads or water use, instead of waiting until the end. Updating totals continuously makes the process more transparent and easier to check. If a value looks wrong, engineers can spot possible measurement or entry errors sooner, while also seeing how the final result develops over time. When using running totals, only add values that share the same units and meaning. Measurements such as rainfall, costs, or material amounts must be comparable before they are accumulated. Begin with a sensible starting value, usually 0, so the total accurately reflects what has been added. This care helps turn small calculations into reliable project-level results. Python code, running totals. Running totals are used to accumulate repeated engineering contributions over time. Each loop update keeps the progress already made, and printing intermediate steps helps verify that the calculation remains reasonable. We define a list of pavement segment lengths measured in meters. Each value represents one segment and will be used to calculate the asphalt volume needed. Keeping the lengths in a list makes it easy to process each segment in turn. The road width is set to 7.5 meters, and the asphalt thickness is set to 0.08 meters. Together, these values describe the road's surface dimensions and are used to calculate the asphalt volume needed for each road segment. Start by setting the total asphalt volume to 0 cubic meters. This gives a clean starting point for adding each pavement segment's volume into one accurate running total. The code prints a table header to organize the results. It names columns for each segment's volume and the running total, making it easier to follow the calculations as the loop processes the segments. The process loops through each road segment while keeping track of its number and length. For each segment, it calculates the asphalt volume from the segment length, road width, and thickness, then adds that amount to the running total. A formatted output shows each segment's volume and the accumulated total, making it easy to check the calculations as they progress. To find how many pavement segments were processed, count the entries in the list of segment lengths. This total can then support later calculations, such as averages or summary statistics. To find the average asphalt volume per segment, divide the total asphalt volume by the number of segments. This shows how much each segment contributes on average to the overall project. The output gives a quick material summary for the project by printing the total asphalt volume and the average volume per segment. Both values are shown to 1 decimal place for clarity, helping confirm that the asphalt calculations match expectations. This script estimates the asphalt needed to pave multiple road segments. Using each segment's length, along with the road width and asphalt thickness, it calculates the volume for each segment and keeps a running total. It then reports the total asphalt volume and the average volume per segment, giving a concise summary of the project's material needs. Maximum tracking. Maximum tracking is a simple way to find the largest value produced during repeated calculations. In civil engineering, this often means identifying the most severe demand, such as the highest bending moment, peak storm intensity, or maximum traffic flow. By checking each result and keeping only the largest one, engineers can efficiently find the controlling case without storing every value. This supports design decisions by ensuring the critical value is used. Maximum tracking means keeping the largest value found so far as calculations progress. You begin with the first measurement, compare each new result to the current maximum, and update it only when the new value is larger. This is useful in engineering tasks such as identifying peak stress or flow depth, but the result is meaningful only when the data use consistent units and are directly comparable. Maximum tracking is most useful when it records not only the highest value, but also where or when it occurs. This context helps engineers diagnose problems and make better design or maintenance decisions, such as locating the station with the greatest pavement deflection or the time of peak water level. In iterative work, update the related context whenever a new maximum is found, so the result identifies the critical condition clearly. Python code, maximum tracking. This example focuses on tracking maximum values across repeated checks. In civil engineering, this helps identify controlling cases, such as the largest beam moments in a set of data. A list is created to store beam positions measured in feet, from 0 to 25 in increments of 5. These values represent key locations where measurements or calculations may be needed. Keeping them in a list makes it easy to access each position or repeat operations across all stations. The code creates a list of bending moments in kip feet for stations along a beam. Each value matches a specific location, allowing the beam's behavior to be evaluated and helping identify where the moment is greatest. The code first checks that the station positions and bending moment values have the same number of entries. This confirms that every station has a matching moment value. If the counts differ, it stops with an error, preventing later calculations from using inconsistent paired data. Begin by using the first moment as the initial maximum and the first station as its matching critical station. This creates a starting reference. So as larger moments are found, both the maximum value and its corresponding station can be updated together. The process pairs each station with its corresponding bending moment, then scans through those pairs to find the largest moment. Whenever a higher moment is found, both the maximum value and its station are updated. By the end, this identifies where the maximum bending occurs along the beam. Set the bending moment design limit to 60, then start a counter at 0 to track how many beam stations exceed that limit. This prepares the process to scan the moments and identify the critical locations where the bending demand is significant. The process checks each moment against the design limit and counts how many exceed it. This gives the number of beam stations where the moment is above the allowed threshold, helping identify possible structural concerns. We track the beam's maximum bending moment as a key structural measure. The report gives the highest moment in kip feet, the beam station where it occurs in feet, and the number of stations where the moment exceeds the design limit, highlighting possible areas of concern. This script reviews beam bending moment data to find the largest moment and where it occurs. It first checks that each station has a matching moment value, then scans the data to update the maximum as needed. It also counts how many stations exceed 60 kip feet, giving engineers a quick summary of critical beam behavior. Iteration counts. Iteration counts help civil engineers track repeated calculations or count items that meet a condition. They can summarize data such as soil samples above a moisture limit or vehicles recorded in a traffic study. As counts build over time, they provide a clear overview of the dataset. Iteration counts should follow clear rules for when they increase. They may count every loop cycle or only cases that meet a specific condition, such as sections exceeding a limit or surfaces failing safety requirements. This distinction separates all items examined from the items needing attention, helping summaries focus on significant engineering issues and supporting better decisions. Iteration counts help check that repeated calculations are complete and reliable. They confirm that expected items such as loads or survey points have been included, and a mismatch can reveal missing data or process errors. Used with running totals, they turn raw data into accurate summaries that support better decisions. Python code. Iteration counts. In engineering checks, count how many iterations occur and track both the total cases and the concerning ones. Then compare these counts with the expected results to confirm whether the checks behave as intended. A set of pavement rut depths is recorded in millimeters: 5, 11, 8, 14, 6, and 17. A 10 millimeter threshold is then used to flag rut depths that are excessive and may need further inspection or maintenance. We start by setting 3 tracking values to 0 before processing the rut depth data. These values count the pavement sections checked, count how many exceed the rut depth limit, and record the maximum rut depth found. Initializing them to 0 ensures the analysis begins cleanly. The process checks each rut depth in the list, counting one more section each time. It also keeps track of the deepest rut found so far, by comparing the current value with the previous maximum and keeping the larger one. The code compares the current rut depth with the allowed limit. When the rut depth is too high, it adds 1 to the count of sections over the limit, helping identify areas that need attention. We first find the expected number of sections by checking how many rut depth entries are in the list. Then we compare that expected count with the number of sections actually processed. If the two counts match, it confirms that every planned section was checked. To find the percentage of sections exceeding the rut depth limit, divide the number over the limit by the total number checked, then multiply by 100. The result shows what share of the inspected sections need attention. The code prints a concise rutting check summary. It reports how many pavement sections were reviewed, how many exceeded the rut depth limit, the percentage over the limit rounded to 1 decimal place, and the maximum rut depth found. It also confirms with a true or false result whether the number of check sections matches the expected total. The script reviews pavement rut depths to find how many sections exceed the 10 millimeter limit. It counts all sections checked, records how many are over the limit, and tracks the deepest rut found. It then verifies the total count against the expected number of sections and reports the totals, percentage over the limit, maximum rut depth, and whether the count is correct. In this lecture, you learned to use for loops to repeat calculations over sequences of engineering values. Use while loops for controlled trial calculations with clear stopping conditions. And accumulate totals, maximums, and counts from repeated civil engineering computations. In the next module, Module 3, we will go over none.
Thank you for your attention. See you all in the next lecture.